Hello, this is MAT221, Calculus 1. This is Mrs. Johnson. This is section 5.2, which deals with the definite integral. We talked in the last section about the indefinite integral, or the general antiderivative of a function. In this particular section, we'll be talking about the definite integral, and we're going to start talking about it in two ways. First of all, using area. So remember back in high school or in pre-calculus where we use summation notation. Remember the sigma notation? The summation from I equals 1 to n of I was equal to 1 plus 2 plus 3 plus 4 up to n. So we would start at 1, I, and then we'd add, right? That would be the summation notation. So we're going to talk about this notation today. In section 5.1, we talked about looking at a function in an interval from a to b. And if we divide this interval into n equals subdivisions, we called the width of each interval delta t, where the width of each rectangle that we were drawing was equal to b minus a divided by n, where b is the end of the interval, a is the beginning of the interval, and n was the number of rectangles that we were drawing. So what we can do now is we can technically take the interval from a to b and divide it up into time intervals. Time sub 0 would be where we start, that would be at a, and then we would break it up. T sub 1, T sub 2, T sub 3 would be the end point of each one of those rectangles or subdivisions. We could say that both the left and the right sums that we found in section 4.8 when we talked about drawing these things called the left and right hand sums can be written more compactly back in, section 5.1, as the LRAM and RRAM can be thought of as a length of a rectangle times its width plus the length of a rectangle times its width, and we keep on adding them all up. And because we were taking the LRAM, remember, which was the left corner of the rectangle was touching the curve, the left corner of the last rectangle would hit at the f of t sub n minus 1. In other words, not the very end at b, the end of the interval, but one less than that. And I'll show you that on a diagram in just a second. And we would notice we would find each one of those rectangles, length times width, length times width, length times width, and then add them up to get our LRAM, or left-handed rectangular approximation method of the area underneath the curve. Now, we can write this more succinctly by using summation notation. We could say this is equal to the sum of I equals 0, where you can see I equals 0, up to n minus 1, of the value of the function at that particular value, multiplied by whatever the width of each interval was, whatever the width of each rectangle was, which was delta t. And we could rewrite the RRAM this same way, where we would say, okay, we would take the right side of the interval was actually this side, at b, which was f of t sub n, multiplied by the width of each rectangle, and then we could add them all up, and then that would be the RRAM. We could write it more succinctly as this summation. Now, the German mathematician Riemann actually took this notation and wrote this notation, and he called them Riemann sums. And we'll talk about that in just a second. But Newton and Leibniz took these notations that along with Riemann and said, okay, this looks really cumbersome to me, these RAMs that we were doing. And what happens if the number of rectangles increases to 100 or 1,000 or 2,000? We wouldn't want to do this by hand. We wouldn't want to actually figure out what this is easily. So this notation can now help us define the concepts leading to delta t approaching 0. In other words, the width of each rectangle approaching a 0 value. Suppose that f is a continuous function from the interval from a to b, and t is in that interval. The definite integral of the function from a to b is written by this notation. So this was Leibniz's notation, actually, and Newton's notation for that thing called the Riemann sum, or the left sum or the right sum, and we would take the average of those two. This is called the definite integral. Now notice it looks like that same elongated S that we saw in section 5.1 and even in section 4.8. And it just now has bounds. Notice it'll have numbers at the top and bottom. This is called the definite integral, and the definite integral will give us a number. The result will be a number. This is the sum of the left hand or the right hand sums with n subdivisions from A to B as n gets really, really large. In other words, as the number of rectangles gets really, really large. In other words, this Riemann sum, this is the left-handed sum, this is the right-handed sum. Newton and Leibniz said, what about if we take the limit as the number of rectangles, this n value, goes toward infinity? That value that we find is called the definite integral. And notice they're the same for both. It is the limit of the left-hand sum or the limit of the right-hand sum as the number of rectangles that we draw heads toward infinity. Now this is very cumbersome notation, and although this book does do a couple of problems where they talk about the Riemann sums, we'll talk about it a little bit, but predominantly we'll talk about this notation, which is the definite integral notation that Leibniz and Newton came up with their studies. So here is the definite integral. This is the integration symbol. This value right here is a constant. It's a number. It stands for the lower limit of integration, or where we want to start looking at our function. The upper limit of integration is b, and that will also be a constant or a number. This function is called the integrand, and whatever function sits here, no matter what we call it, whatever function sits next to an integration symbol, it sits next to that squiggle, will always be thought of as a derivative function. It's the derivative of some function. It's actually the derivative of the antiderivative function that we talked about in section 4.8. Now, you can kind of see where this notation came from. Let me go backwards to the last slide. The notation that they came up with here was that this whole part right here, the limit as n goes to infinity of this summation from starting from A and going to B, here's the function, so you can see the functions right there. Notice it's very similar to the Riemann sum. And they use dt as the delta t. So it's actually saying, Newton says, let's sum up, so he uses big, long, elongated S. Let's sum up all the rectangles from A to B and do the length of each rectangle, which was the value of the function at each one of those places, multiplied by the width, which was delta t. So that's where he came up with this notation for the definite integral. So the definite integral is the integral from a to b of f of x dx is going to be a number. And it doesn't depend on x. Matter of fact, we can use any variable we want to, as long as the function is the same. It doesn't matter what the variable is. We could say, let's find the definite integral from a to b of f of x dx, or let's find the integral from a to b of f of t dt, or let's find the integral from a to b of f of r dr. It doesn't matter what variable we use. All we care about is what function we're looking at and what are the bounds of that function. So because of that, often this variable that we use in integration, because when we talk about definite integrals, we're going to get a number, not a mathematical expression, we call it a dummy variable. Now, this guy called, again, Bernhard Riemann that we talked about, he was a German mathematician. He was a constituent of both Leibniz and Newton, studied in Germany. And he came up with that notation we looked at in the last slides, this Riemann sum notation. What he said was, as I goes from 1 to n of f of x sub I star, that was his notation, delta x. This was called a Riemann sum. And actually, Leibniz and Newton developed this Riemann sum into their definite integral. So we'll give Riemann a little bit of credit here. When Leibniz chose the notation for the integral, he chose the ingredients as reminders of that limiting process. So in general, we write the Riemann sum as just the definite integral. We replace the sigma notation and by the elongated s. We replace the x sub I with the little star by just x. And we replace delta x with dx when we change from a Riemann sum to a definite integral. Now, I really don't know why the book has us do this much, but I will see. I'll show you a couple of examples here. Express this Riemann sum as a definite integral on the interval from 0 to pi. So what we're going to do is we're going to write the limit and the sigma notation. We're just going to change that to an elongated integration symbol. Every x sub I is going to be changed to just x, and delta x is just going to be changed to dx. So if we wanted to write this Riemann sum as a definite integral, we would simply rewrite the function and then know that our bounds are from 0 to pi. So my answer would be this Riemann sum can be rewritten as this notation simply gets replaced by the integration symbol. Our bounds are from 0 to pi, and our function simply gets rewritten with regular x's, and the delta x gets replaced with dx. This part on the left is the Riemann sum. This part on the right is called the definite integral. They are considered equivalent to each other. Now, we still haven't figured out how to calculate it other than to use Mathematica or some other tool on our calculator. But for right now, we just want to talk about this thing called the definite integral. So how do we compute the definite integral? How do we find that value, that area underneath the curve, between the curve and the x-axis? Now, we could manually just increase the number of intervals that we want. But this is where the computer and the calculator is going to help us a lot. I'm going to give you a R-sums program to put on your calculator when I see you in class. But also I'll show you how to use Mathematica to do this also, to find these values, because it's quite tedious to just continue to increase rectangles as we go along. By the way, if we looked at this particular curve, this first value would be called t sub 0, then t sub 1, t sub 2, t sub 3, t sub 4, all the way up. This would be t sub n minus 1, and this would be t sub n. Notice I have an LRAM drawn here, and you can see the left corner of each of the rectangles is hitting the curve. So you see with the LRAM, we go from t sub 0 as our first length, then t sub 1, then t sub 2, then t sub 3, all the way up to t sub n minus 1. Notice that? Notice it's not t sub n, which is the last. Notice I don't use that length. I don't hit the curve there. I hit the curve here at t sub n minus 1. That's where that notation comes from the Riemann sum. So I'm going to show you in this video how to use Mathematica to do this, but we'll also use programs on our calculator to help us draw these and find these definite integrals until we get to section 5.3 where we can actually do them ourselves by hand. So the definite integral as area. When f of x is above the x-axis, when I have a function that is greater than 0, and a is less than b, then the area under the graph of f and above the x-axis between a and b will give us the value of the definite integral. For instance, if I showed you this curve that I just had here, and I drew like 1,000 rectangles here, you can see all those little rectangles I drew. So this blue area, whatever that area happens to be, will be the value of what this thing is called the definite integral. Now this makes sense to us as we go through, and I'm going to stop this video here to get in and talk a little bit more about how and why this makes sense from what we've talked about earlier in the semester.